The nucleus of every atom in your body should not exist. That's not a metaphor. That's not a dramatic way to open a lecture. It is a straightforward physical statement. And if you've never heard it put that way, it's because most chemistry education quietly skips over it, moves on to electrons, orbitals, bonding, the parts that feel useful, and leaves the center of the atom sitting there like a problem nobody wants to address. So let's address it. A nucleus is a cluster of protons packed within roughly 1 femtometer of each other. 1 femtometer is 10 to the negative 15 meters. That's so small that if a proton were the size of a marble, a hydrogen atom would be about half a mile wide. At that distance, marble to marble distance, for protons, the electromagnetic repulsion between two positive charges is approximately 230 newtons, applied to an object with the mass of a proton. That's not a gentle push. That's the kind of force that should scatter the nucleus into individual protons the instant it forms. And yet, it doesn't. Every nucleus heavier than hydrogen is holding together right now. In the water you drank this morning, in the carbon in your bones, in the iron in your blood, something is winning against that repulsion. And most people have never been told what it is. I find that strange. I find it strange that we spend so much time on the electron, on its orbitals, its energy levels, its role in bonding, and so little time on the thing that makes the atom possible in the first place. The electron is the chemistry, fine, but the nucleus is the reason there's anything there to do chemistry with. The model most people carry around in their heads is Rutherford's. A tiny, dense nucleus in the center, electrons orbiting around it like planets around the sun. Neat, visual, easy to draw. Rutherford himself knew it was wrong. Within months of proposing it, he understood that a charged particle moving in a circle radiates energy, which means the electron should spiral inward and collapse into the nucleus in a fraction of a second. The solar system atom shouldn't last long enough to form a molecule. Quantum mechanics eventually resolved that for the electrons. But the nuclear problem, the protons repelling protons problem, that one doesn't get resolved by quantum mechanics alone. That mental picture we all inherited, the nucleus as a stable little ball, sitting quietly at the center, it quietly smuggles in an assumption that the nucleus is just there, that stability is the default. It isn't. Stability is the result. Something is actively producing it, every moment, at a scale and speed that has no analogy in everyday experience. There are 4 fundamental forces in nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. You've probably heard of the first 2. You've possibly heard that nuclear forces exist. But the strong force in particular is almost never explained to people outside of physics. And that's a loss, because it's genuinely strange. The strong nuclear force does not act on electric charge. Charge is irrelevant to it. It acts on a property called color charge, carried by quarks. And it only operates at ranges below about 1 femtometer, not weaker at longer ranges, absent. Think about what that means. Imagine a magnet that is overwhelmingly powerful at 1 centimeter and at 2 centimeters does absolutely nothing. Not weaker, not a gentle tug, nothing. That is the operating range of the strong force. Once 2 particles are more than roughly a femtometer apart, the strong force between them effectively vanishes. Within that range, though, it is roughly 100 times stronger than electromagnetism, which is why it wins. 2 protons, brought close enough together to enter that range, are held there by a force that dwarfs the repulsion, trying to separate them. The electromagnetic force is still there. It's still pushing. It simply loses. The neutron matters here. Neutrons carry no electric charge. They don't add to the repulsion between protons, but they do participate in the strong force. In a large nucleus, neutrons act as a kind of buffer. They contribute cohesion without contributing repulsion. This is why, as you move up the periodic table, the ratio of neutrons to protons in stable nuclei increases. Hydrogen, 1 proton, no neutrons. Carbon, 6 protons, 6 neutrons. Lead, 82 protons, 126 neutrons. The ratio isn't arbitrary. It reflects the balance the nucleus is maintaining between two forces operating on different rules. Now, I want to say something carefully here, because I think precision matters more than confidence when we're near the edge of what's understood. We call it the strong nuclear force. We've measured it. We've mapped its behavior, quantified its strength, described its range. We've built technologies, nuclear reactors, medical isotopes, particle accelerators, that depend on understanding it. All of that is real. But what I just described, the strong force acting between protons and neutrons, that's actually not the fundamental story. That force is a residual effect. The proton is not a fundamental particle. It is made of 3 quarks, and those quarks are bound together by gluons, which carry the strong force at the quark level. The force we observe between protons, the thing holding the nucleus together, is essentially the overflow of the force binding quarks inside each proton. It leaks out, and the leaked force is strong enough to grab the neighboring proton. The analogy that helps me: imagine 2 neutral atoms, no net charge, and yet at close enough range, they feel a weak residual electrical attraction. Van der Waals forces, because the charge distributions inside them are not perfectly uniform. The force between protons in a nucleus is something like that. Not the fundamental interaction, the residual of the fundamental interaction, one level deeper. Which means when someone asks what holds the atom together, the honest answer involves going at least 2 layers below what's visible. And at the second layer, quarks, gluons, the theory called quantum chromodynamics, the mathematics becomes in places genuinely intractable. I'll come back to that. Radioactive decay. Let's talk about what actually breaks. Most people understand that some atoms are radioactive and some aren't. Fewer people understand why mechanically a nucleus decides, if that's even the right word, to shed particles. It isn't a malfunction. It isn't random in the sense of being uncaused. It is what happens when the balance between the strong force and electromagnetic repulsion becomes untenable for a particular nuclear configuration. Alpha decay. The nucleus ejects a cluster of 2 protons and 2 neutrons, a helium-4 nucleus. That specific combination is extraordinarily stable on its own. The nucleus doesn't just throw off whatever it can. It sheds a coherent, stable structure. That specificity tells you something. The physics isn't chaotic. It's finding the nearest stable state. Beta decay is stranger. A neutron inside the nucleus converts into a proton, and in doing so emits an electron and a particle called an antineutrino. The neutron, isolated outside a nucleus, has a half-life of about 14 minutes. Inside the right nuclear environment, it can be stable for billions of years. The environment changes the physics. The same particle, different context, completely different stability. I think about that when people talk about atoms, as if they're like little solar systems, fixed and mechanical. The interior of a nucleus is not a clockwork. It's a negotiation, binding energy. This one matters. The mass of a nucleus is measurably less than the sum of the masses of its individual protons and neutrons. Not by much, a fraction of a percent, but measurably, reproducibly less. That missing mass is the binding energy. When protons and neutrons came together to form the nucleus, they released energy, and that energy had mass, which left with it. Einstein's E=mc² is not an abstraction here. It is a measurable mass deficit that you can weigh if your instruments are precise enough. Getting that energy back requires putting it in. You have to add energy to break the nucleus apart. Fission is exactly that. A large, marginally stable nucleus absorbs a neutron, becomes unstable, and splits. The fragments fly apart, carrying the binding energy as kinetic energy. Heat. That heat is what a nuclear reactor captures. That energy is what was released over Hiroshima in August 1945. Same physics, wildly different applications. The nucleus doesn't have opinions about how you use the energy it releases. Here is where I want to be honest about what we don't know. Quantum chromodynamics, QCD, is our best theory of the strong force at the quark level. In some regimes it is extraordinarily accurate. It predicts the behavior of quarks in high energy collisions with remarkable precision. In other regimes, specifically at the low energies where nuclei actually form and exist, the equations become computationally intractable. We cannot solve QCD analytically for systems with more than a few quarks. What we do instead is discretize space-time onto a grid and run numerical approximations on supercomputers. We call it lattice QCD. It works imperfectly, approximately. It is not a closed-form understanding. The confinement problem. Quarks are never observed in isolation. Every time we've tried to separate two quarks, in particle collider experiments, in any experiment ever conducted, the energy required to pull them apart instead creates new quark-antiquark pairs from the vacuum before the original quarks separate. They are permanently confined. We observe this consistently, universally. We do not have a mathematical proof of why confinement must occur. It is one of the 7 Millennium Prize problems, $1 million unclaimed for a proof of quark confinement. The answer might be in someone's notebook right now. It might not be found for 100 years. And then, above all of this, there is the larger problem that doesn't get said enough. We have two frameworks that describe nature at different scales. Quantum mechanics, which governs the nucleus, the atom, particle physics. General relativity, which governs gravity, space-time, the large-scale structure of the universe. Both are extraordinarily precise in their domains. They have not failed a single experimental test in over a century of combined use. And at the mathematical level, they are mutually inconsistent. They cannot both be exactly right. Something deeper is underneath them that we haven't found. The atom you're trying to understand is described by a theory that works, and a theory that works, and no one has written down the single theory that contains both. I want to say something about my own work, because it's relevant here in a way I didn't understand at the time. When I was measuring radioactivity from pitchblende, working through the systematic question of which elements were active, how active, whether the activity correlated with anything chemical, I was treating radioactivity as a property, something the atom had the way it has a mass or a color. It was intrinsic, fixed. I measured the ionization intensity from uranium salts and found it was proportional to the amount of uranium present and independent of its chemical state. Combine it, dissolve it, heat it, bind it. The activity didn't change. I concluded correctly that radioactivity was an atomic property. What I didn't have, what no one had yet, was any picture of what was happening inside the atom that produced that activity. The nucleus wasn't discovered until 1911, 7 years after I received my first Nobel Prize. The proton wasn't named until 1920. The neutron wasn't discovered until 1932. I was measuring the output of a mechanism that wouldn't be described for decades, and the part that took longer to absorb, radioactive decay, cannot be changed by chemistry. You cannot heat uranium and make it decay faster. You cannot dissolve radium chloride and slow the emission. You cannot apply pressure, change the bonding, alter the environment in any chemical sense, and affect the rate of decay by any measurable amount. The nucleus is simply not accessible through chemistry. It operates on its own rules, at its own scale, on its own schedule. That was a surprise, not a disappointment, a genuine scientific surprise. I had built a career on chemistry. The idea that there was a regime of physical reality that chemistry couldn't touch, couldn't alter, could only observe, that was new territory. It still is, in a sense. Let me close with something that stays with me. The strong force operates on a time scale of 10 to the negative 23 seconds. That is 100 million times faster than the fastest process in chemistry. There is no instrument anywhere, no detector, no camera, no particle accelerator that observes the nucleus in the act of being held together. Everything we know about the interior of the nucleus, the quarks, the gluons, the force exchanges, the binding energy, we infer from scattering experiments, from decay products, from mass measurements, from mathematical predictions that tell us what we'll find before we look. The thing itself, in the act of happening, is not observable. Every stable atom in existence is a negotiation between forces that have never been united in a single equation. The hydrogen atom in a glass of water sitting on your desk right now, its single proton is being held together by gluons exchanged between 3 quarks, a process described by a theory we can only solve approximately, running on computers that didn't exist 50 years ago. And that proton has been stable, doing exactly that, since the early universe. Billions of years of a process no human eye has ever seen. A single proton, 1 femtometer across, 3 quarks, in constant exchange, gluons flickering in and out of existence, carrying the force that keeps the whole arrangement from flying apart, stable for longer than the Earth has existed. And not one person in the history of physics has watched it happen. That is what holds the atom together. And we are still, in the deepest sense, figuring out why.